Hello, welcome to my presentation. My name is Phan. My co-authors are Dudek and Moshe Vardi. In this paper, we propose a unifying framework for weighted model counting using dynamic programming. Our framework is faster than 4 existing weighted model counters on over 500 benchmarks out of the almost 2,000 benchmarks we tested. We start with a brief overview. Model counting is to compute the number of satisfying assignments of a Boolean formula. This problem is sharply complete, which is quite hard. Model counting has several applications, including the automation of medical diagnosis. A Boolean formula is often given in conjunctive normal form, CNF, which is a conjunction of clauses. To compute the number of models of a CNF formula, we can employ bottom-up dynamic programming. For that, we need an intermediate computation tree where each leaf node corresponds to a class and each internal node corresponds to the multiplication of the children, followed by the elimination of a set of variables. We formally call the intermediate computation tree a ProjectJoin tree. Starting with a CNF formula, we go through a planning phase to construct a ProjectJoin tree. With that, we go through an execution phase to compute the model count of the original formula. We develop a modular model counting framework that combines a planner with an executor to make a model counter. For example, we deconstruct a DPMC, an existing model counter, into two components: a planner that uses heuristics from constraint programming CP, and an executor that uses algebraic decision diagrams, ADDs. Similarly, we deconstruct TensorOrder, another existing model counter, into a planner that uses tree decompositions and an executor that uses tensors. Of course, we can mix and match planners and executors to create crossover model counters. Interestingly, one of these crossover model counters outperforms both existing model counters. Now we conclude the overview part and transition into the technical part of the presentation. First, we take a closer look at the model counting problem. A CNF formula is a conjunction of clauses. We can make a truth table where each row corresponds to a Boolean variable assignment, for which the formula evaluates to either 0 or 1. If it is 1, we say that the corresponding variable assignment is a model of the formula. The model count of a formula is the number of satisfying assignments. Although this is for unweighted model counting, our approach can be easily extended to literal weighted model counting. Please see our paper for more detail. One approach to solve model counting is search, which is a DPML-like exploration of the solution space. A representative model counting tool for this approach is Cache. A second approach to model counting is knowledge compilation, which compiles a CNF formula into a tractable form. Representatives for this approach include Mini-C2D, C2D, and D4. A third approach to model counting is dynamic programming, which solves overlapping subproblems. Representatives for this approach are DPMC, TensorOrder, DPDP, and others. One of our contributions is to unify the model counters in the dynamic programming approach. To do that, we introduce ProjectJoin Trees. Taking a closer look at ProjectJoin Trees, we see that given a CNF formula in a ProjectJoin tree, a leaf node corresponds to a class, and each internal node is labeled by a set of variables to be projected away or subbed out. To do model counting on a ProjectJoin tree, we perform bottom-up valuations of the nodes. Each leaf node corresponds to a clause which can be interpreted as a pseudo-Boolean function. For example, the blue leaf node corresponds to a pseudo-Boolean function over the variables x1 and x3, and the possible outputs are 0 and 1. Similarly, the orange leaf node corresponds to a function over x1 and x2, and the gray node x2 and x3. For an internal node, we evaluate it as follows. For example, take a look at this internal node. First, we multiply the children. That is, we multiply the blue function by the orange function. The product will be a pseudo-Boolean function over 3 variables, x1, x2, and x3. But then we project away x1 or somehow x1. That leaves us a pseudo-Boolean function over 2 remaining variables, x2 and x3. We can do the same thing for this root node, and after the projection of x2 and x3, what remains is a constant pseudo-Boolean function whose value corresponds to the model count of the CNF formula. We developed a modular model counting framework which combines a planner and an executor to create a model counter, going from a CNF formula to ProjectJoin Tree, and finally to a model count. We have seen earlier that we deconstructed a DPMC and TensorOrder to existing model counters to make 2 pairs of planners and executors, from which we can create 2 new crossover model counters. We call this whole framework DPMC, or Dynamic Programming Model Counting. One advantage of decoupling the planning phase and the execution phase is that we can create new crossover model counters which may outperform existing model counters. Another advantage is that we can separately develop planning algorithms and execution algorithms. We take a closer look at the planning phase and the 2 implemented planners. First, we focus on the HTB planner. Given a CNF formula, we can construct a Geifman graph, also called a primal constraint graph. In this graph, each vertex corresponds to a variable in the CNF formula, and 2 vertices are adjacent if the corresponding variables appear together in a clause in the CNF formula. From a Geifman graph, we can construct a ProjectJoin tree using an iterative bottom-up algorithm called HTB. HTB is called a one-shot algorithm because it produces exactly 1 ProjectJoin tree for a CNF formula. HTB uses traditional CP heuristics such as MCS, LexP, LexM, and MinFill. We also use bucket elimination and bouquets method to order the clauses given a variable order. The second planner, LG, uses tree decompositions. In a tree decomposition, each node corresponds to a set of vertices in the Geifman graph of a CNF formula. This tree decomposition has to satisfy some technical conditions. Given a tree decomposition, the planner LG constructs a ProjectJoin tree in a top-down recursive manner. LG is an anytime algorithm because it produces better and better join trees if given more time. To do this, LG takes advantage of the anytime tree decomposition tools, FlowCutter, HTD, and Tamaki. Note that tree decomposition has been used in other application domains, including join query optimization. Now we Switch to the execution phase and the two implemented executors. Recall that in a ProjectJoin tree, the valuation of a node corresponds to an intermediate computation. For example, if we do bottom-up dynamic programming on this ProjectJoin tree, the valuation of this internal node is a pseudo-Boolean function over the variables x2 and x3. This function can be represented with an algebraic decision diagram, ADD. In this directed acyclic graph, a solid arc indicates that the corresponding variable x2 is assigned 1 on this arc. A dashed arc indicates that the corresponding variable x2 is assigned 0 on this arc. We can see that this ADD represents a pseudo-Boolean function over x2 and x3, and the possible outputs are 1 and 2. ADDs are a sparse data structure because they take advantage of the logical structure of the pseudo-Boolean functions so that the representation is compact. In this work, we use the ADD package called CUDD. We switch to the second executor that uses tensors. In this context, a tensor is a multi-dimensional array. This includes a scalar, a list, or a matrix. In this work, we use dense tensors. That means we represent the 0 entries in a tensor explicitly, even if there are many of them. In this work, we did not consider the use of sparse tensors. For the experiments, we use the tensor package NumPy. Now we go to the experimental section. We have almost 2,000 benchmarks for weighted model counting. About half of these benchmarks come from the Bayesian inference class. The other half come from various other domains, including planning, circuit design, and scheduling. To do this, we use a Linux cluster allowing 30 gigabytes of RAM and 1,000 seconds for each model counter per benchmark. This is a cactus plot. For each of these 4 lines, an XY point on the line means that the corresponding solver can solve X benchmarks if the timeout is Y seconds per benchmark. Observing these 4 lines, we can see that across both executors, the planar LG, which uses anytime tree decompositions, is better than the planar HTB, which uses one-shot CP heuristics. Also, across both planars, the executor DMC, which uses sparse ADDs, is better than the executor tensor, which uses dense tensor. Now we add 4 more lines to this cactus plot, which correspond to 4 existing model counters. We can see that the existing model counters are comparable in performance to the best 2 combinations of the framework DPMC, which use ADDs as the executor. In fact, DPMC as a framework, including all 4 combinations of planners and executors, is fastest on about a quarter of the benchmarks. To visualize this difference, we add 2 more lines to the cactus plot. These 2 newly added lines are the VBS lines, standing for Virtual Best Solvers. This is VBS1, which simulates running all actual solvers in parallel. This red dotted line is VBS0, which includes all 4 existing model counters, but excludes all 4 DPMC model counters. By looking at the horizontal gaps, we can see how much Adding DPMC to the portfolio improves the virtual best solvers. To summarize, we developed a modular model counting framework combining a planner and an executor, which goes from a CNF formula to a ProjectJoin tree, and finally to the model count of the original CNF formula. We can deconstruct existing model counters in the dynamic programming approach into components, a planner and an executor. And we can make crossover model counters from these components. For future work, we plan to add to the planning phase fractional hypertree decomposition. For the execution phase, we plan to use database tables as in the model counter DPDB. Once again, the code and experimental data are available on our public GitHub repository. Thank you for listening.